Hello everyone, welcome to session 4 of this training course. Today, we're going to explain the different types of motors we offer and what the nomenclature on the nameplate means. I'll summarize some common points of each motor family so it's easier to understand their differences. Each motor we manufacture must have a nameplate on it. There's limited space on the nameplate and some information is required to be there, so any remaining information not on the nameplate can be found in the order details. Let's decode this example nameplate from the top down. I will mention that this information is specific to the motor nameplate. If the motor is attached to a gearbox, there will be an additional nameplate on the gearbox, and it won't contain all of this motor information. So you do have to look at the correct nameplate if you need gearbox or motor information. The first thing you'll see is the model type. We'll break down what these letters and numbers mean later on, but what I really want you to know about the model type is that it only describes the unit generally. It doesn't provide any specifics about it. If you remember from the past training sessions, I said our motors and gearboxes are based on modular platforms, and there are millions of different combinations possible. Since each order is unique, it's not possible to capture all of the details with a model type alone. So the very next piece of the nameplate that is the most crucial part is the serial number. This is a unique number for each mechanical and electronic order that we ship out. We can look this number up and see all the order customizations to know exactly what unit you have and all the parts it was assembled with. There are tools on our website and we have a mobile app where you can enter the serial number to get additional details about the unit. If you are calling into our support line, you'll need to have this serial number available so we can look up the specific information you need. The first 2 digits of the serial number are the country where the unit was manufactured. The middle 10 digits are the actual order number and the line item the unit was a part of. The third set of digits reference which unit this is, since it's possible to have identical gear motors on the same order. The last 2 digits are the year that the unit shipped out. In this example, this would be 2010. Before we get too far from the top of the nameplate, I want to show you this logo above the model type that says FS04. This is a marker to indicate that the unit was assembled with some part that meets functional safety. This could be a mechanical brake, an encoder, or a combination of parts. If you see this marker and are needing to perform mechanical service to the motor, you will need to be careful because if you disassemble the unit, it could void the functional safety rating. Oftentimes, when a functional safety part is needed to be replaced, such as a brake, the unit will need to be sent to your local SEW assembly center to replace the part so the functional safety rating is maintained. Here is a list of the different FS markers you may see. The most common ones are functional safety brakes and encoders, or a combination of both. Now this nameplate is in German, and it's very possible that you will have nameplates in different languages because a lot of manufacturing equipment is made overseas. Even though the nameplate is in a different language, the units will all be shown in an easy to identify way. For example, the rated speed and torque of this motor is shown here. The unit R/min means rotations per minute, and the unit Nm is Newton meters. Here is the rated voltage and frequency of this motor. The units are volts and hertz. Now you may be thinking this is an odd voltage and frequency for a motor. Well, this example nameplate is for a DRL motor, which I'll talk more about later, but these motors can only be operated on an inverter, so this is the only way to have a voltage and frequency relationship like this. If the motor was built with a gearbox, then this is the reduction ratio of the gear unit. The lowercase unit I always means the gear ratio with our nameplates. If the motor was built with a brake, this is the brake voltage that would need to be landed on the rectifier to convert AC to DC voltage. The unit VBR means the voltage of the brake rectifier. As a side note, our brakes only work with DC voltage, so you would not want to land AC voltage directly to the brake without a rectifier. Otherwise, that will damage it. The nameplate will often show the type of brake rectifier that we shipped with the motor, and that is shown here on the nameplate. Finally, just like electronics, gear motors also have thermal ratings. These ratings will vary depending on the type of oil, bearings, and grease the unit was assembled with. So, if you have an application that has extreme ambient temperatures, like freezers and furnaces, you'll need to check the nameplate to make sure the unit is compatible with the temperatures it'll be installed in. Let's look at some of the different standard induction motors that we offer. The first series was called the DT or the DV motor. The name changed depending on the horsepower rating of the motor. This series is now discontinued, but if you've been using SAW motors for decades, it's likely one of the older units is this DT or DV motor. Next, we have the current DRS or DR2S motor. This is the successor to the DT-DV motors. The DR2S motor is the second generation of the DRS series, and it was just announced this year. So this is the newest version that you could see. And these motors are rated for IE1 standard efficiency. The most common standard motor you will see is our DRN motor. This motor meets an IE3 premium efficiency rating. Each country has their own power efficiency regulations, and these are becoming more strict. Starting in 2016, the United States required motors larger than 1 horsepower to be premium efficient. So any new equipment you have that has a motor 1 horsepower or greater is likely a DRN motor. Because of this 1 horsepower rule, the only way to offer a DRS motor is when it meets an exemption in the regulation, such as being less than 1 horsepower. This year, we are starting to offer the DRN motor in less than 1 horsepower sizes because premium efficiency is starting to be required for the small motors as well across the world. So we're getting ahead of the curve on the premium efficiency rules. Now I want to give you some helpful points about our standard motors. You may remember from the first training session that a standard AC induction motor is called an asynchronous motor. It is possible to operate these motors across the line with plant voltage or with an inverter controlling it. Oftentimes, when operating a motor across the line, you have to swap 2 power supply phases to reverse the motor's rotation, and this is okay to do with a standard motor. Voltages will vary all over the world and even application to application if the machine has a power transformer on it. AC motors will have many different voltage ratings they can be built with. The motor stator can also be rewired to swap between a high voltage rating and a low voltage rating. The motor's windings could have a different high and low voltage winding pattern. With our motors, these can range from Y and delta, Y and double Y, or delta and double delta. You would need to check the nameplate to determine what the stator configuration is and what voltage range it supports. The DR motor is modular, and if you compare the DRN motor to the DRS motor, they look identical. The only way to tell them apart is to look at the model type on the nameplate. Since the DR motor is modular and shares some parts across the whole platform, they can be very simple or complex depending on how it's ordered. In the DRN motor example here, you can see it has an extended fan guard to house a motor encoder, and instead of having a flange like the DRS motor, it has mounting feet. Here is an example model type for a DRN motor. This is a complex example, but it is possible to have this many options added to the motor. The model type always starts by the family of the motor. All current standard motors we offer will be in the DR product family. The newest version of those will show DR2. The letter that follows tells which product line the motor is a part of. In this example, the letter N means the premium efficient motor. These numbers are the frame size and stator length. These will vary depending on the voltage and horsepower rating the motor has. Next is the pole count of the motor. If you remember from the first training session, a 4-pole motor will have a synchronous speed of 1800 RPM, and if we account for slip, the actual shaft speed will be around 1770 RPM. The BE5 means that a mechanical brake has been added to the motor. The 5 is the size of the brake, and this number increases or decreases with the motor size. HR is an acronym for hand release, and this is an arm that is added to the brake so it can be released manually without brake voltage for maintenance scenarios. You do have to be careful with the manual brake release because if the load was suspended in the air and the brake was manually released, the load would fall because there is no voltage present on the motor to support the load. If the motor is attached to our gearbox, it has to have a mating flange for that, so the FG is the flange that fits our gearbox. The ASB8 is a quick plug connector to connect power to the motor. We have numerous different connector options and wiring possibilities, so this will change depending on what's ordered. TH is a type of motor thermostat in the stator. It will connect to the inverter with 2 wires that provide a closed circuit signal until the stator temperature gets too high, which causes the circuit to open. The ES7S is one of our most common encoders that we offer for our DR motors. It provides an incremental sine and cosine signal for very accurate speed and position control. There are numerous options here too for different encoder types. The letter V, which is a forced cooling fan, is a powered fan that can provide constant cooling even if the motor is switched off. This is helpful in high temperature applications and ones where the motor starts and stops frequently. Lastly, this is just an example, so there are other combinations of options I haven't mentioned. If you need higher speed and torque out of the DR motor family, we have a special motor called the Asynchronous Servomotor. I've already mentioned it, but it is a bridge between a standard motor and a servomotor. That bridge is created by redesigning the stator windings and rotor to give higher torque and speed when operated by an inverter. We've had this style motor around for a long time. The original version was named CT and CV. These motors were offered alongside the DT and DV motors, so you may notice the naming similarity there. This motor is now obsolete, so it is being replaced to the DRL or the DR2L motor, which is the newest addition this year. The DRL motor is based on the same modular platform as the DRN motor because it shares a lot of the same parts like brakes and encoders. It also has a feature called the dynamics package. The obsolete CT and CV motor didn't have this, but the DRL motor can have different size rotor shafts to support higher or lower torques within the same frame size. The dynamics package 2 will offer the highest torque, so this is often how it is ordered. Just like I did for the standard motors, let me summarize some points about these asynchronous servos. These motors will look just like a standard motor, but they are different in their stator and rotor construction, so they are operated differently. The terminal blocks of these motors will look just like the standard motors, and it's easy to mistake that it's okay to change it from delta to Y or vice versa. But these motors are wired from the factory for the correct voltage and frequency, and it shouldn't be changed. These motors have to be operated on an inverter because of their voltage and frequency relationship, so you shouldn't swap motor phases to reverse the rotation. There is a parameter in the MOVIDRIVE for rotation reversal, so you don't have to do that with the motor phases. These motors can only be used on high voltage applications, So that means it's not possible to operate this motor on a 230 volt application. These motors will not have a horsepower or kilowatt rating on their nameplates. Just like permanent magnet servo motors, these motors are rated for constant torque up to a maximum speed, such as 2100 or 3000 RPM. This is why the nameplate will show a rated torque and a peak torque value with speeds that are different from standard motors. The model type of the asynchronous servo will look almost identical to the standard motors that we just stepped through. There are some obsolete versions, but currently these are going to start with DR or DR2. The only identifier that will be different in the model type is this L that shows it's the asynchronous servo product line. The 90L will still be the frame size and stator length. These motors only come in a 4-pole version, so this number won't change. And the options that follow will be the same as what's available for the standard motor. The BE5 is a mechanical brake. FG is the mating flange for our gearbox. The TF is a different type of motor thermostat that provides a variable resistance for the motor temperature. And the AS7W is a high-resolution, multi-turn absolute encoder that we offer for our DR motor family. The last motor we just looked at shares some qualities of a servomotor, so let's discuss the permanent magnet servomotors that we offer. The first servomotor we offered was the DY series. This motor is now obsolete, but there are many of them out there still running machines. The DY was replaced to the CM servomotor that was launched in 2002. The CM motor hasn't been discontinued yet, but it is an old design. The CM servo is very common because it has been around for 18 years. Another type of servomotor that we offer is called the CMP. This motor was released in 2010 as an alternative to the CM motor because it is capable of higher torque in a smaller form factor. As you've seen so far, we are releasing updates to the induction motors this year. The servomotors are also getting a new version this year called the CM3C. It's named CM3 because it's the third generation of the CM motors and it's available alongside the CMP motor. This new motor is a design mixture of the original CM motor and the CMP motor. The CM3C is an alternative that is better suited to higher load inertia applications. You may remember from the first training session, when I introduced servomotors, I said that they aren't suited for every installation. Some applications can have high load inertia, which can be challenging for the servo to control because its rotor shaft has less mass than an equivalent induction motor. The CM3C motor opens up the ability to give the benefits of servodynamics to a higher load inertia application because it has a larger rotor mass than an equivalent CMP motor. However, the CMP motor can output higher torque in a smaller form factor, but with a less massive rotor, which means less inertia. So you do have to weigh the needs of the application to choose between the CM3C or the CMP servo. The easiest way to identify a servomotor from an induction motor is its shape, and it doesn't have a self-cooling fan. The CM motors have a smooth housing instead of cooling fins that you'll see on an induction motor. However, it is possible to have a cooling fan on a servo, but it has to be externally powered since servos don't have a shaft extension out of the back to attach a fan. Let's summarize some specifics about servomotors. The technical name of a servo is synchronous motor, but in this training, I've also called it a permanent magnet motor. So if you decide to call it a servo, synchronous, or a permanent magnet motor, each one of those is correct. The servo will only come with one wiring configuration on the terminal block, and it shouldn't be changed because it can cause the motor to have erratic behavior. This means it has to be ordered for the correct inverter voltage. A 230 volt servo will have a different stator than the 400 volt version, so this can't be changed in the field by rewiring. Still on the topic of wiring, if the servo is turning the wrong direction, you can't swap the motor phases from the inverter to reverse the direction. This will cause the servo to have erratic behavior or draw high current. Alternatively, you have to change the direction of rotation with a parameter in the inverter. Not all inverters can operate a servomotor. For example, our older MOVIDRIVE A can't operate a CMP servo because it's not designed for it. When an application is being upgraded from a DY servo to a CMP servo, we have to make sure the application is using at minimum a MOVIDRIVE B with the correct firmware so it can control it. If it still has an older version MOVIDRIVE, then we have to upgrade the inverter as well. I mentioned it in the last training session, but uniquely with servos, the resolver or encoder have to be aligned with a correct degree of offset to the rotor shaft to work properly. Let's look at an example model type for a servomotor. The type of servo will be listed as the first few characters. The numbers that follow will be the frame size, which corresponds to different torque capabilities instead of kilowatt ratings. BP is a type of holding brake used on servomotors. There are other options that can be here for different voltages and styles as well. The PK is a temperature sensor that's wound into the motor stator that operates on a linear resistance to the motor temperature. If you have an older MOVIDRIVE B, the inverter firmware would need to be upgraded to be able to evaluate this resistance. The AK0H is an absolute encoder option the servomotors can have instead of a resolver. Lastly, SB1 is a plug connector for motor and brake power and the encoder. If this servo didn't have a brake, then the connectors would be called SM1 instead. Another option is KK, which is a conduit box instead of plug connectors. Just like the previous types of motors, the servos are modular, and this is just an example, so it's possible to encounter something in your model type that I haven't mentioned. Now that I've shown you what to look out for on the nameplates, let's see if you can find the information on these real-world nameplates. I'll give you 10 seconds between each question that shows up to see if you can find the information on both nameplates. Then I'll reveal the answer. All right, what is the rated speed of these motors? Did you find it? I'm going to show the answer now. The standard motor is 1758 RPM, and the servomotor is 4500 RPM. Let's go to the next question. Both of these motors have gearboxes. Can you determine the name of the gearbox? I haven't shown you what the gearbox model types are, so if you aren't sure where it's at on the nameplate, that's okay. The standard motor has a FT77/G gearbox, and the servomotor will be installed on a K77 gearbox. The reason the K77 is at the bottom of the nameplate instead of being with the CMP model type is because this servo probably wasn't shipped with the gearbox attached. This is common when ordering replacement motors or if the gearbox and motor are built in different assembly locations to complete the order. If you're keeping track of points, here's an extra credit one for you because it's somewhat tricky to find in this example. Can you determine the gear ratio of both units? Were you able to find the ratios? If you remember, I said the unit for the gear ratio is represented by a lowercase I. The ratio of the standard motor is down here in the corner, showing 33.74. You could also determine the ratio by dividing these two rated speeds. The 52 that follows after the motor rated speed is the gearbox output speed. If you divide these two speeds, you will get 33.81, so it's just an approximation, but it's close to the real ratio. The K77 gearbox has a ratio of 12.36, and it's included in this added line down here at the bottom of the Servomotor nameplate for the gearbox that this motor is supposed to be installed with. All right, let's go to the next question. What is the rated voltage and frequency for these motors? Let's reveal the answers. The standard motor is rated for 460 volts at 60 hertz, and the servomotor is rated for a system voltage of 400 volts at 225 hertz. Servomotors have to be operated on inverters, so that's why it shows a system voltage instead of a rated voltage. You may notice that the standard motor has its volts and hertz units placed before the value, and the servo has its units placed after the value. This is just the way some nameplates are designed. The units can be spaced slightly away from the value or can be placed before it, but the corresponding unit is always printed horizontally with a value, so you do have to scan left and right to find the proper unit if it's not directly beside it. Here's the next question. What is the brake voltage of each motor? The DRN motor has a brake rectifier voltage of 460 volts AC, and the CMP motor has a brake rectifier voltage that ranges from 432 volts AC to 484 volts AC. This is another extra credit question because it's somewhat challenging to determine unless you're familiar with our rectifier models. So if these motors were supplied with rectifiers, what is the model type? All right, let's reveal the answers. The DRN motor was actually not shipped with a rectifier, so this is why it says none. The acronym BCU stands for Brake Control Unit, so the customer would need to supply their own method to control the brake. The CMP motor was supplied with a BMK-B 1.5 rectifier. This is a rectifier that mounts in the electrical cabinet and it has an internal relay controlled by the inverter to switch the brake voltage on and off. Let's look at the last question. Can you determine the feedback device these motors were supplied with? Let's look at the answers. The DRN motor was supplied with an EI7C encoder. This is one of our low resolution encoders that outputs 24 pulses per revolution that's built into the fan on the motor. And the CMP servomotor was supplied with a RH1M resolver. If you were keeping track of points, how did you score? Did you score less than a 5? Or did you get everything correct, including the extra credit, and got a 7? Maybe you had trouble with only one nameplate and got the other one correct, so you can award yourself a half point if you want. If you missed some questions, that's okay, because it takes time to get used to inspecting nameplates and determining what information is available to you. Okay, we have reached the end of our 4th session. In this session, we went in depth with understanding the different models of the motors we offer. We went over examples of the different motor nomenclatures you can encounter. We ended this session by quizzing if you can identify important information from real-world nameplates. In the next session, we will go in depth with the motor encoders and the brake rectifiers that we offer. We'll also discuss electrical wiring topics and how to troubleshoot the electrical connection of the mechanical brake on the motor. Thank you for your attention. Take care and have a good day.